Welcome to all of you. We now uh, discuss the answer of MCQ 2020 biomathematics paper. First question is an ecosystem following logistic growth model. Initial population was 900 with growth rate constant value 0.1. If the carrying capacity of the ecosystem is 1000, what is the instantaneous rate of change of population? Option 4 is the correct answer. So, the logistic growth model is given by dndt equal to r1 minus n by k into n. And the solution of the logistic growth model is given by nt equal to n0k whole divided by n0 plus k minus n0 e to the power rt. Here, n0, the initial population density is 900 is given, and the environmental carrying capacity is 1000, k equal to 1000, and the uh, growth rate is constant, which is equal to 0.1. So putting all these in this equation, so we get nt equal to 9000 by 9 plus e to the power minus t by 10. Now, instantaneous rate of growth means value of dndt limit at t tends to as t tends to 0. So we have to find dndt when t tends to 0. Now differentiating this nt, we get with respect to t, we get dndt equal to this expression is this, which is equal to 900 e to the power minus t by 10 and 9 plus e to the power minus t by 10 whole square. And putting t equal to 0, because dndt equal to what when t tends to 0 gives the instantaneous rate of growth. So this is 9. Answer is 9 and option is 4. Next question. Steady state x star equal to 5 for the equation dx dt equal to 3x1 minus x by 5 is first answer asymptotically stable. So steady state x star equal to 5 for this equation is asymptotically stable. Here the equilibrium points are x star equal to 0 and x star equal to 5 because dx dt equal to 0 gives this equation and equal to 0, and we get x star equal to 0 and x star equal to 5. And let the right hand side expression of dx dt is equal to fx. So dx dt equal to fx, so fx equal to 3x1 minus x by 5. We find f dash x differentiating with respect to x, we get 3 minus 6x by 5. Now f dash 5 equal to minus 3. So this is negative. So x star equal to 5 obviously asymptotically stable because we have the following theorem. X star is an equilibrium point of the nonlinear first order equation dx dt equal to fx. The equilibrium point x star is locally asymptotically stable or unstable according as df dx at the point x star is less than negative, then it is locally asymptotically stable, and if df dx at the point x star greater than 0, then this is unstable equilibrium point. So answer is asymptotically stable, first answer. Next question. C. The Holling type 2 functional represents Holling type 2 functional represent option correct option is 4 hyperbola, because Holling type 2 functional response can be described by phi n equal to Cn by A plus n, where C is the maximum killing rate and A is the half saturation constant. And if we plot phi n against n population density and phi n vertical axis and n is the horizontal axis, then we get this is the type of hyperbola. So this is the functional response called hyperbolic functional response. So correct option is 4. Next, if R with the per capita growth rate and K with the environmental carrying capacity, then in the density dependent equation, dndt equal to Rn Fn. For environmental regulation, the function Fn should satisfy. Correct option is 2. F0 equal to 1, Fk equal to 0, Fn less than 0 when n greater than K. If we take for interest logistic growth model, so dndt equal to Rn1 minus n by k. Obviously, comparing with the given equation, we get Fn equal to 1 minus n by k. Given equation dndt equal to Rn Fn, so obviously we can take Fn equal to 1 minus n by k. Now, Fn equal to this, so F0 equal to, put n equal to 0 here, so 1, this is 1, F0 equal to 1, and F1 equal to 1 minus 1 by k, and Fk equal to 1 minus k by k, put n equal to k in this equation. So, Fk equal to 0. So, in the option 2, F0 equal to 1 and Fk equal to 0. And Fn is 1 minus n by k, which is negative, this, which is negative, Fn is negative when n is greater than k. Yes, Fn is negative, means 1 is less than 1 by k, that is k is less than n, so n is greater than k. So n is greater than k when population density is greater than k, carrying capacity, environmental carrying capacity, then we get Fn equals to Fn in less than 0. Fn is negative when population density is greater than population carrying environmental carrying capacity k. So our correct option is 2. Next question, a system has the characteristic equation lambda plus 4k lambda square plus 5 plus k bracket lambda plus 10 equal to 0. The range of k for the stable system is k is greater than 0.46. Here we apply Routh-Hurwitz criteria. This we know if the characteristic equation lambda cube plus a1 lambda square plus a2 lambda plus a3 equal to 0, then all roots of 1 have the negative real part. That is, real lambda is negative if and only if a1 is positive, a3 is positive, and a1 into a2 minus a3 is positive. And then if the negative real part have all roots have negative real part, because from eigenvalues we can get the nature is stable, equilibrium point is stable when the negative real part, that is real lambda, is less than 0. Here a1, comparing with the given equation, a1 equal to 4k and a2 equal to 5 plus k and a3 equal to 10. So obviously 10 is a3 is positive and a1 is positive, this 4k, this 4k, 4k greater than 0, k is positive here. So a2 equal to this, and so we find a1 into a2 minus a3 equal to this expression, quadratic expression from the left hand side. We get this expression after simplification, we get k square plus 5k minus 5 by 2 is greater than 0. So the from the quadratic equation, k square plus 5k minus 5 by 2 equal to 0 gives the value of k by Siddharth formula, minus b plus minus root over b square minus 4ac divided by 2, and we get this equal to 0.46 and minus 5.46. We call it this 0.46 alpha, and minus 5.46 is called beta. So this inequality can be written as k minus alpha into k minus beta is greater than 0, obviously. So these two factors, product of these two factors is positive. So we have either k minus alpha is positive and k minus beta is positive, or k minus alpha is negative, k minus beta is negative also. So from this, k is greater than alpha, k is greater than beta, and so k is greater than 0.46 and k is greater than minus 5.46, and combiningly we get k is greater than 0.46. And from the second condition, k is less than alpha, k is less than beta, we get k is less than minus 5.46, k is less than 0.46. So we get k positive value. So k is positive when k is greater than 0.46 is the correct option. K is greater than 0.46. Next question. This question is the reaction diffusion model is the out of syllabus from 2022. So we avoid this question. And next question G. In the discrete model, nt plus 1 equal to 1 plus r nt minus r by k nt square. R and k are positive parameters, and the non-trivial equilibrium is asymptotically stable for here. Actual answer is 0 less than r less than 2. So we can choose either 1 or 3 or both. You can get full credit from either 1 or 3 or both. You can choose this. So here discrete model is this given by for fixed point in star we put nt plus 1 equal to nt equal to n star. So put this from the equation, we get this expression. So n star equal to 0 and n star equal to t, and we say n1 star equal to 0. This n1 star is first equilibrium point, trivial equilibrium point n1 star, and second non-trivial equilibrium point n2 star equal to kk is the carrying capacity, environmental carrying capacity. Now let nt plus 1 equal to fnt. So this right hand expression is called fnt. So omit t. So fn equal to 1 plus r n minus r by k into n square. So differentiating with respect to n. So f dash n equal to 1 plus r minus 2 r n by k. And we find the f dash n at the point non-trivial equilibrium point k. So f dash k equal to 1 plus r minus 2 r. This is equal to 1 minus r. For n star equal to k asymptotically, locally asymptotically stable, then modulus of f dash k must be less than 1. So 1 minus a, modulus of 1 minus a less than 1. So minus 1 less than 1 minus r less than 1, and hence we get a minus 2 less than minus r less than 0. That is 0 less than r less than 2 is the correct answer. Next question, the transcritical. Next question, for the pre-predator model, dx equal to rx1 minus y, dy equal to my1 minus x, where m are positive parameters and the equilibrium 0 0, trivial equilibrium 0 0. Here there are two equilibria. One is 0 0 and other is 1 1. We get two equilibria points. So first we discuss for the equilibria, trivial equilibria 0 0. Actually, there is no correct option. Actually, answer is unstable node. Unstable node. So you explain details for this unstable node. Here, dx equal to fxy and dy equal to gxy. Say. Then fxy equal to rx minus rx into y and gxy equal to my minus m in x into y. So del f del x and del f del y, del g del x, del g del y, and we get four first order partial derivatives, and you get the Jacobian for the system. This is equal to del f del x, del f del y, del g del x, del g del y, and value of the Jacobian matrix 2 by 2 matrix is this, given by this. And for the trivial equilibrium point 0 0, we get the Jacobian is put here x equal to 0 and y equal to 0. So we get the 2 by 2 matrix Jacobian at the point 0 0 r 0 0 m. Obviously this diagonal matrix, so the eigenvalues are r and m, and the r m are positive parameters, so both are positive. So we get the trace t equal to greater than 0, delta is greater than 0, this d discriminant is obviously greater than equal to 0. So 0 0 is an unstable node. Is the correct answer. And if other equilibria, non-trivial equilibria, 1 1 is also a non-trivial equilibrium point, and the value of j at the point 1 1 is given by this, the two matrix, this value is the value 0 minus r minus m and 0. And so t trace this 0, this is equal to 0, and determinant of j at the point 1 1 equal to minus rn. This is obviously negative, and d discriminant is r 4 rm, obviously greater than 0. So 1 1 is a saddle point. if we take the help for the page plane plotter, and then clearly you get value of r equal to 0.5 positive value and m equal to 0.2 say. Then x dash equal to 0.5 into x star into 1 minus y, and y dash equal to 0.2 star y star 1 minus x. And then clearly from the graph phase plane, from the phase plane, this axis is this x-axis and this is the dx dt. So this sorry this is the phase plane, sorry, the phase plane, two-dimensional phase plane. So this we get this 0 0, origin is the 0 0. Here clearly this is the unstable node, and this point 1 1, so this point 1 1, so you get this is the saddle point, and because this arrow is towards this and this arrow is repels from this point 1 1 point, and 0 0 point is this unstable node clearly from this phase diagram. Next question is this bifurcation parameter, transcritical bifurcation with mu as bifurcation parameter. You can can be found in the system. Option, correct option is 2, x dot dx dt equal to mu x minus x square. This transcritical bifurcation, actually this is the transcritical bifurcation, supercritical transcritical bifurcation. If we put mu x plus x square is also another transcritical bifurcation, is called subcritical transcritical bifurcation. So expansion, this is the equilibria, x dot equal to 0 gives x star equal to 0 and x star equal to mu, and if x is equal to the right hand side of the x dash mu x minus x square, so we get mu x minus x square. F dash is equal to this, f dash equal to 0 equal to mu, f dash mu equal to minus mu. There are two cases when mu is negative, so we get f dash 0 is negative, so x star equal to 0 is a stable equilibrium point, and if dash mu is positive, so x star equal to mu is unstable, is an unstable equilibrium point when mu is negative. And case 2, when mu is positive, then x star equal to 0 is unstable unstable equilibrium point, and if dash mu is negative, so x star mu is stable, locally asymptotic stable equilibrium point. So if we plot phase portrait along the x-axis is x and y-axis is x dot. So for the case mu less than 0, there are two equilibria, is mu and 0. 0 is the stable and mu is the unstable. When mu equal to 0 is half stable or semi-stable, and for mu greater than 0 we get two equilibria, is mu is stable and 0 is unstable. So if we plot this mu axis along the horizontal x-axis and along the vertical y-axis the x at x, when we plot this is this the solid line, this x equal to 0 gives the stable equilibrium point when mu is negative, and this after 0 bifurcation point 0 0, this line is dotted line, so x star equal to 0, x star equal to 0, that is the equilibrium x star equal to 0 is an unstable equilibrium. And other equilibrium, x star equal to mu, non-trivial equilibrium, when mu is negative, clearly this is the unstable equilibrium dotted line, and after bifurcation point 0, this equilibrium is stable equilibrium, So the stable becomes unstable and unstable becomes stable. So the stability extends that stability. This. Next question, steady state x star equal to 3 of the difference equation xn plus 1 equal to xn e to the power 3 minus xn is option, correct option is 3, unstable. Here correct option is unstable. So here equilibrium points are x star equal to 0 and x star equal to 3. So if x equal to x into e to the power 3 minus x, and f dash x equal to this, so f dash 0 is e to the power 3, obviously greater than 1, So x star equal to 0 is an unstable equilibrium point. And f dash 3 equal to minus 2. F dash 3 equal to minus 2. So modulus of f dash 3 equal to 2, which is greater than 1. So extra 3 equal is an unstable equilibrium point. So there are two equilibrium points, but both are unstable equilibria. So a pretty interesting case for this, a period doubling bifurcation occurs at x star equal to 3. And for interest, this Ricketts logistic equation xt plus 1 equal to xt e to the power r minus xt when r is greater than 0. There are two equilibria, x1 star equal to 0 and x2 star equal to 0, and x1 star equal to 0 is unstable, and x2 star equal to r for locally asymptotic stable if 0 less than r less than 2. Here in this case, here r equal to 3. Here r equal to 3 for so from Ricketts logistic equation r equal to 3. So obviously this x2 star equal to r is locally asymptotic stable when 0 less than r less than 2. But here r is 3, so obviously this is unstable. Now from the graph this fx equal to x e to the power r minus x. This when you put r equal to 2.1 and initial value x0 equal to 1, if we put this, then by Cobweb diagram you get this point. This if you change this r equal to 2, r equal to 2, this also this equilibrium triple equilibrium 0, and this equilibrium is equal to r. Here r equal to 2. So r equal to 2. So here this r equal to 2. This equilibrium non-trivial equilibrium 2. Then also we see that this 0 and 2 also unstable equilibrium. If value is 1.5, then clearly from this diagram, Cobweb diagram, this point r equal to 1.5. So clearly this diagram, this 0 is the 0.0 is unstable, but this r 1.5 is stable equilibrium, locally asymptotically stable equilibrium. If r equal to greater than if 2, then we get say 2.5, then this. If r equal to 3, put here r equal to 3 and this. So clearly this equilibrium point first is intersecting point with the diagonals, this origin, and other intersecting point is these 3. So this is the equilibrium point, non-trivial equilibrium point, and this is the when r equal to 2, and this is the r equal to 2, and we get this type of this. So ultimately this cobweb, this from this to this ultimately this and this. So this is the period doubling here. So because period doubling means if this point is say P and this point is Q, then from the graph this point is P, so this x-axis, this point is P and this point is Q, and corresponding for this point Q we get corresponding point is FP. This point is FP, this point is FP, so this point is FP, and corresponding for this point Q, we get this point is FQ from this point FP. So AP equal to FP and P equal to FQ and Q equal to FP, then this is called period doubling. Option, and this is the last question J. So we conclude this lecture. Thank you.